Okay, so today we're going to be talking about tree-backed sets and maps, and that just means a set data structure or a map data structure where the internal representation of the data is in the form of a tree. And we'll see that it's not really too different, the representation if it was a set or if it's a map. In the map case, our internal nodes will just have one extra element. Um, so we'll note that distinction once we get to the put method and the get method. But first, let's talk about the motivation on why tree-backed is a good idea for a set and a map. Um, and so, for one, we'll see after we do our insertion and retrievals that getting things back in sorted order is actually very easy with these trees. Whereas if you use, like, for example, a linked list back set or a map, then it would be a little bit more difficult. You'd have to perform a sort on top of the underlying linked list or array list. The other thing we'll see that we're going to have very fast runtimes for our put and our get methods. Um, I guess I'll write get, or it could be contains, or I guess contains or get. Contains if it's a set, and then get if it's a map. Um, So we'll see that our runtimes are going to be way quicker if we have a tree-backed set or a map as compared to like a linked list backed set or map or an array list backed set or map. Memory, we'll also see we'll have much better memory. And then we'll talk about the limitations kind of when we're going over these two methods. So let's start with how we insert into a tree. So there's this pretty cool visualizer. If it's like the first thing that pops up if you type in like tree data structure visualization. It's this website cs.ufca, and then you would just click binary tree, this one, and then insert things. So I've inserted the following things here, in this specific order: 5, 10, 6, 1, 4, 7, 2, just by clicking over here and inserting it. So let's see if I wanted to add a new thing. Let's say I wanted to add a new element. Um, let's do 0. Okay, so and I've adjusted the speed to be pretty slow. So let's see how this data structure inserts. So we see we first compared to this root node, and then we chose to go left. Um, so the red circle kind of, if we go back and maybe go a little slower, we did 0. So it compares the element in question to the root node, and then it chooses to go left. And that's because the thing we're adding, this 0, go back again, this 0 is less than this root. And that's all you need to know is just what the value of the root is to determine if 0 needs to be on the left side of that, or sorry, the thing you're inserting needs to be on the left side of that or on the right side of that. So because 0 is less than 5, we chose to go to the next node, which is 1. And now we're going to do the same thing. Since 0 is less than 1, it needs to go on its left side. And since there was nothing on its left, it just gets a new child. The 1 gets a new left child, and it's just the 0. And that's maintained at every single node in the tree. So for example, if we go to this node 4, we'll see that on its left side, it has a 2, which is less than its value, 4. And if you go here, you have a 6, and its right child is 7, which is greater than 6's value. And that happens throughout the entire tree. And you can also kind of say different things about um, like a node versus all of the things on its right subtree. So for example, this 5 node, its right subtree has a root 10, and then that 10 has a left child, which is a 6, and that left child has its own right child, which is 7. And since they're all on the right side of this 5, that means they're all greater than 5. Because if any of them were less than 5, that must mean that they belong on this side of 5, not on the right side. So we know that any node to the right of a particular to any node that's on the right subtree of a node has to have a greater value, or if you want to call it key, than the node you're like looking at. So in this case, this 5. Um, okay, let's try inserting something. If I wanted to insert something right here, let's see what kind of number I would want to insert. So I definitely want to have that number be on the right of 5. So it definitely needs to be larger than 5. Um, okay, now I would compare so the node in question is at least 5. or at least bigger than 5, so 6 or above. And then it needs to be on the right side of this 10. So as long as it's 11 or larger, it'll go here. And we can test that. If we do 11, it'll compare to 5, go to its right child, and then since 11 is bigger than 10, it'll go there. We can try doing a different number. Instead of 11, if we do, say 20, the same thing would happen. Then it's just the same comparisons, so nothing changes there. Um, okay, let's see. Now let's say we wanted to get something that's over here on the right side of this 4. So it would need to be less than 5, but greater than 1 and greater than 4. So it would need to be between 5 and 4. So I'm not sure if this lets us do integer. Yeah, no, so you can't do decimals here. So there's actually no number you can pick that would be between 4 and 5, since 4 and 5 are just one integer apart. And actually, same thing for this case with the 6th child. The 6th left child would have to be greater than 5 because it's on the right side of 5, but less than 6 because it's on the, we want it to be on the left side of 6. And there's no integer that satisfies that, so there's no way to put something here. Let's see, we can put something on, for example, the right side of the 7, and let's see, it would have to be greater than 5, but less than 10, greater than 6, and greater than 7. So it has to be greater than 5, greater than 6, and greater than 7, but less than 10. So the two candidates are either 8 or 9. So if we put 8 in there, it goes right, left, right, and then finally right. We could have also done 9. That would have done the same thing. 9 is greater, then less, greater, and again greater. So those are the two numbers that could work there. Okay, so we've gone over the insertion procedure. It's just checking, it's basically just determining whether you need to go right or left at a particular node. In the actual code, in terms of like the get helper method, the actual logic for like inserting like when this 7 got a new right child, that's something you should be able to figure out on your own. Maybe walk through a smaller example with maybe 3 nodes and see how each node's left and right child should change when you like insert something. In this case, it was the seven node that changed. Everything else stayed the same in here. Okay, so that was our insertion procedure. Let's talk about the time complexity. So here there's kind of two cases. This is a pretty good tree in the sense that the number of levels is pretty small compared to how many nodes there are. One thing like, let's see, an example of a bad tree is if I insert it in a particular order, like increasing, for example. If I did 1, and let me up this animation speed. If I did 1, 2, 3, 4, 5, 6, and so on, I think you can see that this tree is kind of degenerating into a linked list. Whereas here we had many different nodes. We had 1, 2, 3, 4, 5, 6, 7, 8, 9. We had 11 nodes here, and our height of the tree was 1, or 1, 2, 3, 4, because the lowest node is 4 kind of hops away from the root node. So 1, 2, 3, 4. So we say this tree has height 4 with 11 nodes, which is not that bad. This tree has 6 nodes and its height is 6. So one thing you'll note in our put method, all the work that gets done is kind of walking all the way to the place where we need to insert the node, and that walking process is what takes all the time. In this case, it was only a few hops. When we inserted the 9, it was just 1, 2, 3, 4 hops. Um, but if this tree was larger, then we might need to do more hops to get to the bottom. So you can imagine if this was, say, like 1,000 long, we would have to do 1,000 hops just to get to the last node to insert something, in the worst case. In terms of best case, you have a tree kind of like this. More generally, it'd be like what we call like a full binary tree. So it would look something kind of like this, where every node is kind of maximally connected. They all have as many children as they can. Um, so it's like, you might also see them being called bushy trees because they're kind of wider than like the tree you see here. This tree is not very wide, whereas this one has many different nodes in just in just 3 levels. In just 3 levels, this one has 1, 2, 2, 3, 4, 5, 6, 7, 8. This one has 16 nodes, whereas this was twice the height, but half the number of nodes. So as you can tell, the height of the tree is what really makes the difference in terms of the two um, methods we support, the put method, and as we'll see, the contains and get method do roughly the same thing. So let's write our two different time complexities. So let's first do the worst case. Okay, worst case, we know that, actually we can put it here. Worst case degenerates into a linked list type structure. So whenever you think of worst case on trees, you should imagine something like this. So it's all on the right, or maybe it's all on the left, or maybe even it alternates right, left, right, left. Just some sort of structure where the height is about linear in the number of nodes that the tree has. Um, so something kind of looks like a linked list, where it's not really using both pointers. Um, and so let's see what the time complexity of put would be here. Well, in the worst case, let's say there's n nodes in the tree. I guess we can put that here, time complexity, where there's n nodes in tree. In the worst case, if someone calls put, then what if it's that very last node that we need to add? So it's like, if, for example, if the numbers were 1, 2, 3, all the way to n, and someone adds n plus 1, then we're going to need to go all the way down. And that's going to be one hop for every level. And since there are n levels to this tree, the total time is going to be theta of n. In the worst case for our put, because our tree would look like this. But in the best case, so in the best case, our tree is what we're going to call bushy. And I guess I can make a note of what this means. What this means is that the height is, height is log n. And the reason it's log n is because this is not, okay, so this is a bushy tree, even though it's not like a full binary tree. As long as it like is pretty close, like in terms of like asymptotics, we still say it's bushy. Um, so because, for example, this one is not quite utilizing its height as well as it could, because this node could be filled in, and then these two nodes could be filled in, this one over here. Um, but for right now, this is essentially bushy. The Each time you traverse down a level, the number of nodes on that level should double, because you have, if you have, for example, let's say you're at this node here, or sorry, this level here, we have 4 different nodes. Then when we go to the next level, a bushy tree would have every node have both children. And so if there were 4 nodes here, the next level would have 8 nodes, because each one of those 4 nodes will have its 2 children. In this case, we only have 2, so not not quite full like this tree, but still close enough. And so you basically have like this sum. I guess we can write it here, because the first level will have just 1 node, because that's the root. The second level will have 2 nodes, because that's like here, these 2 nodes here. The next one has 4 and 8, and it just keeps doubling. 1 plus 2 plus 4 plus 8 plus 16, all the way to n. And each one of these kind of like pluses is like dividing a level. So we just want to know how many numbers are there in the sequence. And the total amount of numbers is log n. So log n numbers in that sequence. I guess this should actually be n over 2. The last level will have half of all of the nodes in the tree. So if you apply the geometric sum formula on this sum, you should get n. Or maybe this should be like n over 2 minus 1. Something like that, something pretty close. But yeah, that's basically why the height is logarithmic in terms of the total number of nodes. And so if your height is log n, then, like we said, the runtime of like the get method is just however long it takes to get to the bottom. So if the tree looks, it's a bushy, it's like this, then it's going to take log n time to get to the bottom. Theta of log n. Okay, yeah. So basically, the worst case and the best case has everything to do with the height of the tree. So which is why we'll see that we're going to want trees that have small heights compared to the number of nodes in the tree. So later on in the course, we'll see how we can kind of avoid this from ever happening um, using different types of trees that will kind of self-balance. So if it ever gets itself into a situation like this, it'll kind of move the nodes around. So it's a pretty balanced tree. But that's kind of out of scope for this homework. We're not going to deal with that. For now, you can kind of imagine we have things like this. Okay. Um, okay, so that's our time complexity. Okay, so now we can talk more about the differences between if you have a tree map versus a tree set. And it's more or less the same thing. Here, this is kind of a tree set. We only see like one value on each of these nodes. If it was a tree map, however, then we're just going to add one sort of extra piece of data to each one of these nodes, which is the value stored in that node. So then you're still going to only use the key to determine whether you should go left or right. And then once you finally get to the node you care about, for example, let's say somebody wants to know what is the value associated with key 2, then you're going to compare key 2 to the key of this node, which is 5. And then you're going to go left because 2 is less than 5. And now you're going to compare the key 2 to this key 1, and that's 2 is greater, so we'll go here. And then the same thing happens here. And then finally, the keys are equal. And as they're equal, you just want to know the value of this node. So no other node that we checked, the 4, the 1, and the 5, we don't care what the values are at all. So the value only matters once you get to the node you care about. And maybe you don't get to the node, like maybe someone called get of like -1. So you'll go left, left, and you'll go left again, and you'll note that there's nothing there. So maybe you have some case in your code where if I get to a null node, then I should maybe return none or null, or maybe throw an exception, or whatever the specification is. Just that's what you would handle it in that case. And when you kind of recurse and see that you see a null node. Um, okay, so that's basically just the difference. It just has each node just has one extra piece of. I'll just put underscore value to note that it's an instance attribute. Um, but in terms of the process of figuring out which node to go to, it doesn't matter at all whether if it was a tree set or a tree map. You're just going to look at the keys of those nodes to jump around. So in your code for your tree map, you shouldn't really care about the value at all until you get to the node that has the same key. So if you're doing something like comparing the values of two nodes, that's not something you should be doing. Just kind of walking over it. Okay, now what to do with duplicates. So here, first we'll talk about what to do with a tree set. Um, and you'll note that from the kind of our definitions of sets that we don't store duplicates. If someone wants to add 5 again, we're gonna, or let's say someone wants to add 20, for example. So we as of at the beginning we don't know that we have 20. So we'll start here, and we know 20 is bigger than 5, so we'll go here to 10, and we know that 20 is bigger than 10, so we go here, and now you see that 20, the key we're looking for, 20, is equal to this node, 20. And it's because it's a set, we don't want to have duplicates, so we can just stop right there. We were not going to add it. We're not going to like add a different edge here and put 20 there. I want to note though that this website actually would do that. It will add a duplicate. I don't know. I think it's on this side. Um, yeah, so this website will add a duplicate. In our cases, we will not be. So that's the one thing that this website's not too good at. For some reason, they have duplicates. Um, okay, so that's what you would do for like a tree set. You would just, whoops, um, ignore duplicates. So what that means is like once you get to node, do nothing. So don't change the key, don't change any left or right branches, just don't change anything. Okay, but with a tree map, it's actually a little bit different. So let's say somebody wants to, so with a tree map and like the put call, where is it? The put method. So for a tree or a tree set, it would be like put some key k. But with a tree map, it would be like put key k and value v, for example. So let's say somebody wants to put at that key 20 some value, and let's just say the values are strings, and they want to put the string dog. So like we noted earlier, we're not going to use the value to compare what child to go to. We're only going to use the key. So the key was 20 that we're looking for. And when we want to insert the value dog, so we see 20 is larger than 5, so we're going to go on its right side. And now we're comparing 20 and 10. We're going to go to its right side. And now we see that we found a node that has the same key. Okay, and then okay, so we're going to start at the root 5, and we'll note that the key we're looking for is larger than this 5. So it was 20, right? So 20 is larger, so we go here, and then from 10 we go here again. And now we found a key that has, or sorry, we found a node that has the same key as the one we were looking for, which was 20. And so all we would do here is instead of doing nothing, like in the set case, the tree set case, we're going to change the value of whatever this used to be to the new value. In our case, we just said dog. Um, so that's the difference in the put call. We just in the tree set implementation, you would just ignore you wouldn't do anything once you found a key, sorry, once you found a node with the same key. But in the map case, the tree map case, you would just change the value. And that doesn't have any different runtime because you still need to traverse up until the node, and then either you do nothing or you change one attribute, which is both constant time, once you get to the node. Okay, here we would just change, I'll say underscore value to note that it's an instance attribute, change value to the one you are inserting. Okay, so that's your insertion, and retrieval is basically the same thing. It's just now that when we get to the node, um, we're not gonna we're not gonna create any new nodes. We're just gonna see if that node exists. So if we get to a null node now, instead of creating a new node, we're just gonna like say return false, like this doesn't exist in the map. So for example, if someone calls, let's say we had a tree set, and someone calls, does this set contain? I'll put these things in your key k. This is also key k. So someone asks, does this set contain 1? So if they want to know if this tree set contains 1, we'll start at the root. And since the key 1 is smaller than 5, we'll go left. And since the key 1 is equal to this node, we'll return true, that yes, we did find that node. Okay, let's see an example where the key doesn't exist. So maybe 11, or let's do 8. So we'll go here, and 8 is greater than 5. So we go to its right node, its right child. 8 is less than 10, so we're going to go left. 8's greater than 6, so we go right. 8 is greater than 7, so we go right again. And we found 9, and 9 is greater than 8, so we're going to go left again. And then we hit null, and like we said, if we hit null, that means that node doesn't exist. Because if there was an 8, it would have to go here. It could not go anywhere else in the tree. It belongs in this exact place. So we can safely say false, this tree does not contain that value. And then if you implemented this with recursion, like using the get helper, then that value of false would kind of bubble up the recursive calls up until the initial call to the get helper method, and the whole thing would be false. Okay, let's see. And that's actually the only place you should ever return false. If you're at a node and that node is null. So you shouldn't do something like if node dot like left dot value equals the key, or sorry, node.left.key equals the key you're looking for. You shouldn't do anything where you're kind of checking in advance the keys of the left and right child. You should instead just recurse on them and then have a case for if it's null. Because if it was null, then you know that it doesn't exist. In that one case I was talking about, or in the thing I said not to, if you do like if node.left.key equals whatever the key you're looking for, then you can get kind of issues with if, for example, this one doesn't even have a left child, so that if statement, if node.left.key, that would be a null pointer exception because you said like node.left, which is null, dot key. So you're basically saying null.key. That causes errors. Usually with any tree method, it's usually you just have the 4 cases you have are if the node you're at is null, then do one thing, and then the 3 other cases are if the node you're at has the same key as the one you're looking for, or if the node you're at has a key that's larger, and then finally if the node you're at has a key that is less than whichever one you're looking for. In each one of those three cases, you do different things, and it depends on what method you're doing. Um, but that's more or less kind of the procedure. So the mostly same. Actually, I actually won't really write notes for that one. It's mostly the same as the put. It's just once you get to the null node, you do something different. And then once you get to the node that has the same key as the one you're looking for, then you also do something different. Okay, let's talk about time complexity. Um, because the retrieval procedure was the same, or almost exactly the same as the insertion procedure, it just differs once you finally get to the node. It does some constant time thing, but just a different constant time thing. The time complexities are going to be the exact same. So we can kind of take what we had here and then just put it here. Um, yeah, it's just because the in the get method, the contains method, all you're doing is just kind of walking over to the node that you want to like see if it exists or not. So in the best case, our tree is bushy, and the node is like the node's at some log height. So like all the leaves here would be at the that height is like log n, whatever, where n is the number of nodes in your tree. And then in the worst case, like here, it's still going to be n because if somebody wanted to see like, does this tree contain n plus 1, then you'll have to keep going down your right branch until you hit n plus 1 or null, and that's going to be n. That's going to cost n that like runtime because there are n nodes in the tree and it's just a straight line like that. Okay, so yeah, those are the same, and then here the differences between this contains and this get, where the contains is for the tree set and then the get is for the tree map. The only difference is what you do once you find the key, once you find the node that has the key. So this again, we'll talk about what we do in the tree set case first. Oops. Okay, yeah, what we do in the tree set case. So in the tree set case, with the contains method just needs to return true or false. So um, when we find the node with the same key, we return true because that means we found it. Whereas in the tree map case, when we find this node that when we find the node with the same key, we return that node's value. Um, yeah, so these are the two different things you do in this case, and then one thing I'll leave an open question here is when we find a null node, and then you can fill in the blank here. Um, it will be different for these two different things because the tree set needs to return a Boolean and tree map needs to return um, whatever the value is associated with that key. So in this case, if you end up at a node that is null, then kind of implementation specific, you should figure out whatever the like specifications are of your tree map. Like if that key does not exist in the map, what you should do, maybe you can just like kind of check like what like for example Java's tree map does. If you call get on a key that doesn't exist, what it does, and maybe you can do that if you want in your get method if you if you reach a null node. Okay, yeah, so that was basically all the different things that we kind of want to talk about for homework 6. That should help you on the implementing the BST string set. So that'll be the what's it called? The put helper method and the get helper. And then as for the other methods, as list and then the bounded string iterator, you should use what we talked about here and the different invariants about trees to help you logic out through uh, how you're going to be able to how you should first of all approach it, and then what data structures you might need, and how to kind of formulate your methods, like if you want to use iteration or if you want to use recursion. Um, yeah. Okay, so that concludes this. Hopefully this helps with the homework and for studying for the tree questions on the exam, I will probably post this on Piazza, this document here. Feel free to comment, and if you wanted to ask a question, you can do that in the Piazza thread. But yeah,